Hello everyone, I am Salman Khan from Oxford Brookes University, going to present our work, A Hybrid Graph Network for Complex Activity Detection in Video, authored by myself, Izzeddin Teeti, and broadly Mohamed Elhoseiny and Fabio Cuzzolin. Detecting and recognizing activities in untrimmed video is a challenging research problem with application to different domains of computer vision such as autonomous driving, surveillance. Temporal action localization methods can be employed to temporally segment these activities, for example, by recognizing their activities and start and end time. However, the temporal action localization methods are limited to short-term mid-duration action which lasts for only few seconds. So, and other drawbacks of temporal action localization is they are mostly focused toward a single actors. For example, in this case, the two data sets of temporal action localization like Thomas 14 and ActivityNet, we can see that the camera is focused toward the actor which actually performing the action. However, in real life, autonomous driving dataset, for example, one of the recently released road, we can see each of the agents are performing individual actions, and their individual actions are collectively called as a complex activity as well. For example, in this case, the complex activity is negotiating pedestrian crossing, where the pedestrians are crossing the road, and we refer them as a complex activity detection. To model this complex activity detection, we propose a method composed of three stages. First of all, we have the input video. After having the input video, we divided the input video into snippets, and these snippets are passed to the feature extraction, the first stage of our framework, where we extract the features. Then these features are passed to the, so we extract the features from the individual from the individual actor as well as the overall scene, and these features are learned through a scene graph network to understand the dynamics or the scene dynamics of the scene, and then pass it to another graph, a temporal graph, which can actually recognize and localize the activity, the complex activity. So let's look into the feature extraction. In feature extraction, we propose a new strategy for extracting the feature, which consists of two steps. The first step is object detection and tracking. First of all, we detect each of the agent using a pre-trained object detector and then track them using a pre-trained tracker. So the object detector is trained on COCO dataset with a deep sort tracker. After tracking them, we extract the feature from each of the individual. So we cropped each of the individual agent or the object, and then we extract the feature from the overall scene using a pre-trained 3D CNN, and also from the whole scene and each of the individual. After extracting the feature, we represent this feature in a scene graph. So first of all, we generate a scene graph using three different topologies. First of all is a star graph. A star graph is where each of the agent is connected to the overall scene feature. The next one is a star topology with also link between agents sharing the same label. For example, all of the agents are connected to the scene graph, and then the agent, for example, the pedestrian is connected to the pedestrian, vehicle is connected to the vehicle, and lastly a fully connected graph where each of the node is connected to all the other nodes. After the graph generation or the scene graph generation, we use a scene graph attention method, for finding the attendance or the importance of each of the nodes over its neighbors. To do this, we adopt a scene graph attention network, in which we are first of all linearly transform the feature using a weight matrix and apply a self attention. After applying a self attention, we forward them to the activation function. For activation, we are using a leaky relu and then pass it to the softmax to normalize all these features. This all step is called as a node attention. When each of the node is attended, we apply a multi-head attention to do it multiple times, h times for each of the node. After doing this, we apply another weight matrix to aggregate the overall feature, because the main aim of having a scene graph or a whole graph is to have a fixed length representation from each of the snippet. After applying this, we forward this to a temporal graph. So in the temporal graph, each scene graph is represented as a node, and they are temporally connected to each other. We apply a graph convolution network to these, which is a 1D graph convolution network, and this output us two things. One is the activity classification, which can give us the label. For example, you can see from scene graph 2 to scene graph 5 we have an activity negotiating intersection, and then from 6 to 8 we have a background class. So it can give us the class for each of the snippet or a scene graph, and then when it is started and when it is ended. We perform experiments on three different types of data set. Firstly, ROAD. ROAD is the first complex activity detection data set proposed in STDGS paper, where they show the performance with three different types method. In this paper, we also re-implement the Tenformer and ActionFormer, the recent temporal action localization method on complex activity for ROAD, to show the fair comparison of our method with the most recent methods. In addition to the ROAD dataset, we also compare our method on the temporal action localization method to show the importance of a method, that it can work in complex scenes, but it can also work as a temporal action localization methods on the data set where they are focused on a single actor. For the comparison, we compare with two different types of method. The methods which are using multi-stream, for example, the optical flow and RGB stream, and only the RGB stream. We outperform all of the method on only using the RGB stream and get a comparative results on also comparable results with the optical flow method. We also compare our method with recent state of the art, for example, Talformer and ActionFormer, where they are using both, for example, the RGB and optical flow stream, but in our case, we are only using the RGB streams and increasingly outperform them when the complexity is increasing. For example, the complexity in our case is complexity of average duration of the activities or average number of agents per snippet. We perform different types of ablation study, for example, the effect of edge nodes, where we can see, for example, not detecting any agents and take the scene features only and how it behaves. In addition, we also perform the effect of edges and aggregation, for example, if we do only a fully connected graph or a star graph or a star plus, and by aggregation and scene we are taking the feature, for example, only the scene features or the aggregated feature from the whole graph. We also show the effect of different sequence length, for example, the sequence length for a snippet, or the effect of a temporal graph length, for example, the whole temporal graph, how many scenes a temporal graph can have. And lastly, we show the qualitative results for all the data sets. That's all. Thank you very much. If you have any questions, please feel free to write it to us. Thank you.